In this lesson, we're going to look at the two main forms of energy, kinetic energy and gravitational potential energy, and how to solve some basic problems with those. So let's look at, first of all, what is energy? And energy is the capacity to do work. And so we're basically continuing along with our work stuff. Energy is going to be measured in joules, just like work is, and it's a force that's moving something over a distance. So kinetic energy is the energy possessed by moving objects. So remember when we did friction, we looked at kinetic friction, so the friction that's caused by things that are as they are moving. So kinetic means moving. And so here's our formula. And it's derived on page 230 to 231. Most of you, I know, don't care, but if you are into caring, have a look and you can see what it is. So we're doing our mass times our velocity squared. So let's look at an example. So we have a 250 gram ball. So that is your cue right there. You need all masses in kilograms, okay? And we have energy in joules, so that's good. What is its velocity? So let's write down what we know. 250 grams, we're going to divide that by 1,000. So move the decimal 3 spots to the left. So we get 250 or 0.250, kilograms. We have our kinetic energy because it's moving. It tells us that it's kinetic energy. And it's asking us to figure out its velocity. So let's write down our formula. And let's go ahead and rearrange so that we can get V by itself. So I'm going to start by getting rid of my fractions. So I'm going to multiply by 2. So then I'm going to have 2ek equals mv squared. I'm going to divide both sides by m. So we have 2ek over m equals v squared. And then we need to square root both sides. So I'm just going to flip it around there for you. And then we're going to go ahead and we're going to put our information in. And then we're going to go ahead and solve. So you get 29.93, and that would be meters per second. And then let's look, this has 3 sig figs. We can say that that has 3 sig figs. So let's round that to 29.9 meters per second. And again, we're not generally going to worry about directions, but in most cases here, stuff's going to be going forward. So gravitational potential energy is a form of energy that an object possesses because of its position. So kind of the easiest way to explain this is a roller coaster. So on a roller coaster, you generally start by going up some giant hill, and then you start going down. So when you are up here, you have high potential energy, low kinetic energy. This can also be seen at the top of a ski hill. So if you're not really into roller coasters, maybe you've gone skiing. When you're at the top of the hill, you have a lot of potential energy because you know as soon as you start down the hill, you're going to speed up. So on a roller coaster, it's very slow. We get to the top. It almost feels like you stop for a second and then you start going down real fast. And so when you get down here, you have high kinetic energy and low potential energy. So the further you are away from the ground, the more potential energy you have. And then the faster you're going, the more kinetic energy you have. And so then you might do these loops, and then you would start back up a hill to get you that potential energy again, which is then converted into kinetic energy. So we're going to look at this in a gizmo in tomorrow's class, where we're going to look at kinetic energy and potential energy and how. So let's look at another example. So here we have our formula for potential energy. Your textbook uses EG. I often use EP. It doesn't really matter. So you've got mass in kilograms. You have G, your acceleration due to gravity, and you have H, your height. So it says determine the gravitational potential energy of a 52 kilogram student who is at the top of drop zone at Canada's Wonderland, 70.1 meters. And we always have our G at 9.8 meters per second squared. So we don't have to rearrange at all. We can just go ahead and put our information in. So we get 35,722 0.96 joules. So when we get such a large number, oftentimes you're going to see the answer in kilojoules. And so we would divide by 1,000 to move our decimal there. So we would get 35.7 kilojoules. And then we could go ahead and we could look at our sig figs. So this only has 2. So let's go ahead and round that to 36 kilojoules. So oftentimes you're going to see the answers expressed in kilojoules. But in order to put it back in the equation, you're always going to need it in joules. So the other thing is just kind of relating what we talked about in the last video with work and the work energy principle. So work net is equal to the change in kinetic energy. And we can express that change in kinetic energy by doing our final minus our initial. So all we're doing is we're just putting in each equation for kinetic energy, and we're just doing it our final minus our initial, because that change, that triangle means change in. So you always do your final minus your initial. So we could kind of do EK2 minus EK1. And then expanded, it looks like that. Let's look at an example of that. So we have a 175 gram hockey puck. So let's write down what we know. And we're going to automatically convert that to kilograms, because you need kilograms. It's at rest, so that means our V1 is 0. It's pushed by a hockey stick on ice, which we're going to assume is frictionless, by a constant horizontal force of 5.6 newtons. What is the puck's speed after 0.55 meters? So to do this, let's look at what we can figure out. So we have a force and we have a displacement, which allows us to figure out a work. So let's go ahead and do that and then see if that helps us get closer to what it is we're being asked to find. So 5.6 newtons times 0.55 meters. So we get 3.08 joules. And then we just said that we can always make work equal to our change in kinetic energy. So that means we can write this as mv2 squared over 2 minus mv1 squared over 2 equals our work. So we have our V1, we have our mass, we're looking for our V2, and we have our work. So let's go ahead and put in what we know. Oh, sorry, I forgot to put my mass in. I am just going to put numbers in because I'm going to guess that most of you wouldn't probably try and rearrange an equation like this. If you are, that's great, but if you're not, that's okay too. So this part is going to go away. So then let's continue solving. So we do 3.08 times 2 to get rid of the fractions, and then divide by 0.175. And then we need to take the square root of that. And so we get V equals 5.93 meters per second. And so then let's go ahead and look at our sig figs. So we have 2, 2, 3. So we want to round that to 5.9 meters per second. So again, just to kind of go back, I was running out of space. So we're going to do the 3.08 joules times 2, hit equals on your calculator, and then divide by the 0.175, hit equals, and then to get rid of the squared, you're going to do the square root. So that's how you do it all in one step on your calculator. So hopefully that has helped with energy. We're going to continue obviously looking at energy during this unit.